All right, this activity titled Reaching for Beads is really going to set the stage here for Chapter 7 and what we're going to be focusing on, which is the different distributions, a population distribution, a sample distribution, and what's called a sampling distribution. And so we're just going to open up here, first of all, with making sure that we're comfortable with a few terms here. The first one is a parameter. Okay, when we talk about a parameter, this is always a number that is describing a population. Okay, so oftentimes we end up using Greek letters of the alphabet to refer to parameters, like that mu symbol represents a population mean. We know this sigma symbol here is representing a population standard deviation. And we know when we use just a plain P, or at least we're going to be introduced to this in this section, a regular just P is referencing a population proportion. So if you were, wanting to know what percent of Americans are considered to have high cholesterol, if you use a P, that means every single American would have been surveyed and had their cholesterol levels measured, and that would be the percentage or the proportion who had high cholesterol in the United States. Okay, an unlikely thing to actually accomplish here. Okay, and so we've talked before about the term statistic, where this is really a number that's describing a sample. Okay, and so when we talk about samples, we're familiar with the X bar symbol, which references a sample mean. And we know if we're using a P with a little hat symbol on it, that's the symbol that means a sample proportion, okay? A sample proportion. So maybe we would choose a random sample from adults who are in the United States, and we would measure their cholesterol levels, and whatever percent or proportion of our sample showed high cholesterol, we would label that with a P hat, denoting that it was a sample proportion. Okay. Something else that we have discussed before is this term bias. That is anytime the parameter, which is really the thing we're trying to measure, we're trying to learn about a population through just our sample. Anytime our parameter is consistently either overestimating or it is consistently being underestimated by our statistic. Okay, so bias means it's got to either swing where most of them are on one end over, or most of the data is on the other end under. If we're talking about it, some being over and a few being under, then that's fine. There's no bias apparent there because it's kind of centering itself right where we would want it to be. So when we talk about an unbiased estimator, okay, an unbiased estimator, that would be a statistic that is not consistently overestimating the parameter, or it's not consistently underestimating it, but instead there's a nice even mix of values that are over and under your estimate. And then what we can conclude is that the true value of the parameter is located in the middle. Okay. This is actually a really powerful idea here, and something that you want to make sure that you are comfortable with is the distinction between these three types of distributions. So we're going to break down these three types of distributions, and it's going to lend itself nicely into this activity called Reaching for Beads. Okay, so there are three types of distributions. The first one is called a population distribution. And so if you could picture that our population is just going to be the numbers, we'll say 1 through 20. Okay, so if I were to put those numbers on equal size slips of paper and put them all into a hat, my population would be all of those values in the population. And then if I were to make a population distribution, the population distribution, it's describing all of the individual values 1 through 20. Okay, everything. Okay, now comparing that to what we would call a distribution of a sample. Okay, notice this is singular here. Distribution of a sample. This is when you are graphing the contents of merely one sample that you have taken from your population. It can be called a distribution of a sample, or it can be called a sample distribution. Okay, not to be confused with the term right next to it called a sampling distribution. But a sample distribution is when you've reached into your population and you're pulling out a particular sample size from it, and then you would graph those individual observations, say, on a graph. So let's just say that we were going to pull out a sample size of 5 numbers from our population, which is 1 through 20. So we have these numbers in a hat. We're going to reach in one at a time. We're going to pull out 5 numbers. We're not going to be replacing them in between our selection here. And you can see I've just kind of listed, here are maybe 3 possible samples that I could get. Okay, you can see here's 5 different numbers. There's 5 other numbers. And this, of course, in between my samples here, I would be replacing these back in between. Okay, but each of these separate things that I have here represents a sample distribution or a distribution of a sample. You'll notice I'm describing, you can see each of the individual observations that I selected. Okay, now the third type of distribution, and this is the focus here in this chapter, is called a sampling distribution. Okay, now what a sampling distribution is it's when you take all of the possible combinations of, we'll say, size 5, since that was my sample size, from the population, and you calculate a statistic. So let's say for my samples, I were then going to calculate the sample mean. Okay, you can see I have that here. Of my first sample here in red, if I were to average those 5 numbers, the average is 12.6. If I were to do that again, the average for my second sample is 11.8, and you can see that 9 is my third sample. Now, what we're talking about here is we're talking about I would keep replacing in between. I would list all the different possible combinations, and there would be a lot of different combinations that I could possibly get from choosing 5 numbers from 1 to 20. Okay, there are a lot of combinations. If I did that and got all the combinations and calculated the sample mean for each of those, what I would then be doing is I would then plot all of those sample means on, say, a dot plot here. This is what I'm looking at here. I'm looking at all these statistics. If I plotted all of those on a dot plot, that would represent what's called a sampling distribution. Okay, a sampling distribution. Okay, now every time you take a sample, we know that you would get very likely a different statistic. You can see that evidenced here in just these 3 samples that I took. Okay, and so as you have these statistics, if you plot those statistics, that is what creates what's called sampling distribution, and it creates sampling variability, where one sample feels like it's varying slightly from the other in terms of comparing, say, their sample means. Okay, so what we're going to be doing is we're going to be examining the shape and the center, the spread and outliers, that's our kind of our CUS acronym, for a sampling distribution. Okay, so everybody is going to be given a bag of 200 beads. Okay, you're going to be given a bag of 200 beads here. And I'm just going to explain this activity to you because I know if you're watching this video, you don't actually have these contents here. But what happens in this activity is actually a really awesome thing. And it kind of reveals this super cool idea in statistics about sampling distributions and how we can learn an awful lot about a population from doing this idea here. Okay, so everyone in class would have been given a bag of 200 beads. Now, 100 of those beads are red. Okay, 100 of them are red. The other 100, I believe, were, I'm not sure what color they were, but there were half of the beads were definitely red. Okay, now the parameter, keep in mind this is the actual proportion, so that's just a P, of red beads is 0.5, and that's because 50% of the beads are red. So we know what the parameter is here. Okay, oftentimes we don't know the parameter for a population, but for this activity we know half the beads in the bag are red. Okay, so what you're going to do is each person is going to draw out 3 random samples of size 20 beads. Okay, 3 random samples of size 20 beads. So they're going to pull out 20. And after they pulled out 20 and placed them on a paper plate, they're going to note what was the proportion in that sample of red beads? Okay, so let's just say that in your sample of 20, maybe 10 of them were red. Okay, well then that would result in a p hat of maybe 0.5. Okay, if 15 of them were red, then your p hat would be 0.75 because 75% of them were red. Okay, so everybody's going to get something different, but we're going to go through and everyone is going to reach in, pull out a sample of 20, calculate the sample proportion of, this is red beads. Okay, then they're going to dump all the beads back in. They're going to repeat that 3 different times. Now, just to make our sampling distribution a little bit bigger here, everybody in the class is going to do this 3 times. We're going to throw it all on the same dot plot here. I went ahead and took 22 samples myself and kind of preloaded this with, when I did this 22 times, these are the different p hats, the sample proportion of red beads. I kind of went ahead and placed those. Instead of putting a dot though, I think it was more effective so that you can see what each dot is actually representing, is I'm putting a p hat symbol acting as my dot so that we can see how frequently each of the sample proportions are showing up. Okay, so in class, this is what we would have gotten. So I'm going to add in some of the p hats that we got actually in class with this activity. I'm going to stack these just on top of the ones that I already did when I kind of did this myself here. Okay, so you can just add these on in. Let's see here, there's 4 more stacked here. 1, 2, 3, 4, 5, 6, 7, 8 more on top of this one. 2, 3, 4, 5, 6, 7, 8. All right, just a few more here to kind of finish this off, and then we can kind of talk about what we're actually seeing here. Now, we didn't actually do what's known as a full sampling, true sampling distribution. A true sampling distribution would be, we'd almost have to mark each of the red beads and number them like 1 through 100 and make sure that we got every single possible combination. Now, since we didn't actually do that, we would call this really an approximate sampling distribution. But this is going to give us a good enough idea here. We want to describe in number 3 what we're seeing on this, and you'll notice I'm calling it an approximation of a sampling distribution. And we're just going to kind of describe and go through CUS, the shape and the center, the spread, and any outliers or unusual values. So it definitely feels like the shape is, maybe we could say, roughly symmetrical. Okay, if I were to draw kind of a curve, over top of this, it has a rough symmetrical shape there to it. Okay, we could say for our center, I'm just going to use the word typical. That's a nice word that means center. The typical proportion of red beads, okay, and I think it's easiest for us to just probably use the median. So if we work through here and try to find the p hat that's in the very center, and I'm not sure right offhand how many p hats we have here, but I do know that the center would fall right here if we worked our way from left to right. The center is going to be located on one of these p hats there that is 0.5. So we're going to say the typical proportion of red beads is 0.50. And then I'm just going to say that the proportions span, this is going to be my spread here, from, looks like the lowest p hat was 0.25 to 0.70 with no apparent outliers. Okay, with no apparent outliers there. Okay. Now, here's what we know. Remember, we actually started this out knowing what the actual true parameter was. The bag had a population proportion of red beads at 50%. When we made a sampling distribution, look at where the center was. It was spot on at that 50% mark. Okay, this is going to lead in really nicely with what we're going to be discussing in this particular section here. It says the variability of an approximate sampling distribution goes down or decreases when your sample size increases. Okay, what that means is we were taking a sample of size 20 beads. If I had everyone reach in and pull out 50 beads for your sample size, what we would notice is that this would shrink. It's still going to center around what that true population proportion is, but it's probably not going to span from 25% to 70%. It might span more from like 40% to 60%, something like that. The variability is going to start to close in from left to right around where that true population proportion is. So it says the full sampling distribution, if we were to do like an actual, all the different combinations, it would really be centered at the true value of your parameter. Okay. Sometimes the statistic is lower, sometimes it's higher, but it will be centered at that true parameter, and that's what we mean when we call something an unbiased estimator. Okay, I believe the next video picks up right here with this idea. It's very short, it just touches on the first example or so, since this video took up so much time, but you will need to watch, I think, the next video 7.1.